So yeah, good evening to all once again. So welcome to week 10 discussion of NPTEL program for our electrical machines 2 course. So I am Sai Krishna Mulpuri, and let's start our discussion on electrical machines 2. Last week we have discussed concepts on the three-phase induction motor and also uh, few concepts on starting of the motor we have discussed, and later we have discussed concepts on equivalent circuit of induction motor and so on. So this week we will be discussing an interesting topic in induction machine, that will be single phase induction machine. So we heard about three phase induction machine. So we have discussed how do an equivalent circuit of an induction machine, which is three phase, will look like, and we have seen many discussions like torque produced in a three phase induction machine, and what are the losses involved, and how would the torque speed characteristics would look like. And then we have discussed how to start the motor and speed control of induction three phase induction motor and so on. But now we will be seeing another category of induction machines, that is single phase induction machine. So it will be interesting to see what exactly a single phase induction machine is, and how it will behave, and what kind of what kind of equivalent circuit will does it have. So yeah, we will be discussing on the discussions of single phase induction machine. So, so a single phase induction machine, constructionally, we can say there will be stator, and also there will be a rotor, like any machine we have, it will have the same thing. But here the difference will be, it will be a single phase machine instead of a three phase. There won't be three different kinds of windings on it, but instead we will have a only single phase winding. So we will see how it will look like. So let's say this is I'm just drawing a rotor of uh, induction machine. Let's say we have some kind of winding here. Uh, this is a short circuited rotor, and we will have, this is the winding. One second. So yeah, so we will be having a winding like this. Let's call this winding as M. We will call this as main and single winding. This is only a single phase winding for a machine. Okay, and usually the rotor is a cage rotor. This cage rotor I have drawn here. Now in this one, we are not seeing three different windings displaced in the space by 120 degrees for a three phase machine, but here we are seeing only one winding. That is, if we want to look this particular winding in a motor, let's say this is the stator of a machine. Let's say we have a slot like this on here, and here we will just have this winding, if this entering like this, and then this will come back like this. So this is what only one winding will look like. Now if we connect this winding to a single phase source, so how it will behave, and what will be the consequence of it. Now I'm trying to say, uh, just let's connect this particular source to a single phase AC source. So yeah. Now what will happen? So will the motor will run, because there's a rotor part we are talking about. Will the rotor rotates, or will the rotor current pass? So that's the question. Now, if you remember our discussion which we have, one second. So if you remember our discussion on during week 5, so we are discussing about how a coil would behave when we give a AC supply to a coil. So when a single phase source is connected to our winding, which we are seeing here, a sinusoidal current will flow through it. So that will happen because the winding we have connected a alternating source, and then through the winding we can see a sinusoidal current will flow through it. So whenever a time varying current is flowing through a winding, it will create field. So that's the immediate reaction which we can say. Yeah. So how does this the field created by this current would look like? What is the nature of this? So this exact point we have discussed in our week 5 discussion. So we saw a wave something like this. If it is this amplitude, and if the amplitude of current is a bit lower, it will be like this. And if it is even further lower, if it like this, if it's a negative, it will be like this and like this, and yeah, like this. So this will be the current amplitude, and this is with respect to time. So if at all a person is standing here and is observing the amplitude of the current at different time instants, he will only see a, a current amplitude pulsating in nature. We even gave this kind of wave a name. This is, if you could remember, you can say that is standing pulsating wave. So this is exactly we discussed. If you want to more details on it, you can visit back our week 5 discussion. So there we discussed if we give an alternating current to a coil, it will create a field, and then the nature of this field will be like a standing pulsating wave. At a single point, if you are observing the amplitudes of the current in space, you will see different amplitudes of a current, that is standing pulsating wave. It's not rotating. That's what we discussed then. Now, will there be a rotor current? That's the question. And the answer would be yes, there would be rotor current. So, because if we consider a single turn here, and through which, so let's say there are many turns, and like this, um, this is a rotor, and let's say we have turns like this. And if you consider single turn, maybe this one, this is cross, and this one is if you consider this single turn through which we are trying to pass a time varying flux, because okay, you can say if we consider this single turn, we can see whenever we are trying to pass a time varying flux. One second. So whenever we are trying to pass a time varying flux through this particular turn, it will induce a voltage, because we studied it. Whenever there is a time varying flux, voltage will be induced, is equals to and d phi by dt. So yeah, if voltage is induced, that proportionally the current will also flow. Now similarly, if you take any other coil in this rotor, so we are being subjected this that coil to a time varying flux. So it will just behave as a transformer whose secondary is short circuited. So it will react to the time varying field, and the voltage will be induced on it, and current will flow. So this, how will the current in the rotor would be distributed? So that's another point of discussion. So this rotor current distribution will be like it will depend on the basic Lenz's law. So it has to oppose the cause at any time. So I can just draw it here so that you have a understanding. So this one, let's say this one is our main winding, which is generating the time varying field. And let's say you have, okay, we have connected this to a supply, and it will be responsible for a current flowing through it, and whatever may be the current flowing, this will be the axis of the field. So whatever it is, so if it is in this direction, if we assume this direction of flux is in this direction, and my rotor the current distribution in the rotor will be in such a way that it will oppose this cause. So this is the direction of the field and of the main field, and my rotor coils will be distributed like this. and it should oppose it. So it will be cross will be here, all dots will be here. This is how my rotor current distribution would be. Now it will be like this, and my flux will be in this way, in this way. So it will just oppose the cause of it, and it will then try to oppose the field caused by the stator. So this is how my current distribution would be. Now okay, now we have answered the two questions. So will the current pass in the stator? Yeah, the current would be passing in the stator winding. It is a standing pulsating wave. And will the current pass in the rotor? Yes, the current would pass in the rotor because we are passing a time varying flux through the rotor, so that the current should pass. And now another question, the main important question is: will the motor rotate? Will the motor rotates? Because if something needs to be rotated, torque needs to be produced. So the question is, will the torque be produced here? So will this motor be able to generate the torque? So we have two fields, stator field is there, rotor field is there, and rotor is there. So the main question comes, will these two produce the torque? So the answer would be no. So because to produce a torque, we know two forces would be at some kind of angle. If it is 90 degrees, we can so it will have a maximum torque, but it should be at some angle to each other so that rotating torque will be produced. But if we see here, both the fields are acting along the same direction. So if it is a stator field in this direction, the rotor field is in this direction, the axis is same. So there can't be any torque produced in this case. Now, this is what any typical single phase induction motor would look like. And by just observing whatever we are seeing here, we can conclude that point. So what is the first point we have concluded? So by only observing, we can say that single phase induction machine cannot rotate. It can't rotate because the fields produced by stator and rotor are acting along each other. And also that is, if my single phase induction motor is having a single winding on the stator and also no any other winding, by seeing we can see already single winding here, and cannot rotate if there is only single winding. So the conclusion is no starting torque. So this is one observation which we have seen. Now there won't be any starting torque. Now another interesting point is, so let's say okay, there is no self-starting ability, so starting torque cannot be produced within this machine. So what I will do, I will just try to rotate the motor, rotate the rotor, or precisely uh, by giving some kind of external force. So let's say some kind of external force I've applied. So I used a prime mover and just gave a clockwise direction external force to my rotor. So to our surprise, we will see that my motor will start picking up speed. Now, if you just give a small external force and leave it, and I can observe that my single phase induction motor actually picks up the speed and settles to some steady state rotor speed NR. Now, in which direction the motor will rotate will depend on the direction in which I am giving the external force. If I am giving clockwise external force using my prime mover, my motor will pick up the speed in its clockwise direction, and it will slowly, the speed will keep on increasing, and it will settle to a rotor speed of NR at some steady state speed. Now, if I give a anti-clockwise external force, my motor behave the same way. It will rotate in the anti-clockwise. So this is interesting point. So the second observation is single phase induction motor has running torque. So we will be looking at the later conditions now, why it is not having a starting torque, and that we saw because the torques are there, and we will see even more mathematically also. We will develop some equivalent circuit and also see at some expressions, and interestingly, we can also observe the same behavior there. So you have to remember this. Yeah, single phase induction motor has a running torque. So these are the two conclusions which we have just derived by just looking at the motor construction and also by the observation. So from these two conclusions, we came to know that, so okay, let's say I have a single phase induction motor. Now I want to rotate it. Now what should I do? So now we came to the conclusion that in order to make a single phase induction motor work, we need to somehow incorporate starting torque into it. So that's clear now. If by some way, if you could able to incorporate a starting torque, then we are going to achieve working condition, because once starting torque is given, there is no question about running torque, because it will then pick up its speed by itself. Now, how we are going to achieve this particular starting torque in the machine? So that we are going to do by bringing another extra coil onto the stator. So yeah, we will see what is that coil, what will the coil do, and we clearly saw that if there is only single coil like this, the field generated by it will rotate, like will induce the field and will generate the field, and my rotor winding will uh, react to that field by passing the current through it, and it also generates some field opposing the stator field. But with only single coil, starting torque would be produced. Now we will achieve this starting torque in my induction machine by bringing another winding along with the stator winding. So that's what we will do. So why are we doing this? Because we know that once I can bring some kind of external means and start produce a starting torque. Now we know our machine is capable of picking up its own speed. So one second. Yeah. Since we are aware of the property of the machine that it can able to capable of picking up its own speed. Now, because it has a running torque, once it picks up the speed, and we will disconnect our extra winding. So that's the idea. So just for bringing the starting torque into the picture, we will bring some additional winding. So that will somehow generate the starting torque. We will look into that. Once my machine picks up the speed, I will disconnect the winding from our machine. So that's the idea. So let's see how it works. So consider we will see that idea of how we can actually do that. So before that, we will discuss some basic two-phase winding fundamentals, so that we will see using a two-phase winding how people are generating the torque. So for understanding the idea, so let's consider a two-phase induction motor that will help us in better understanding of this. So let's consider a balanced two-phase induction machine or motor. So because from this idea, we will see how the torque is being generated in a two-phase machine, then we will implement this idea to the single-phase machine as well. But everything we will follow, like what exactly a single-phase machine is and what is a two-phase machine is. Now I'm drawing the two-phase induction machine. Like we say, we have a balanced two-phase machine, so there will be two windings. This one and another winding. Let's say like this. Yeah. So let's name this winding. So yeah, we know this is rotor, and this is winding M, and this is winding A. We will see the terminology later, but for now, this is what names we are giving it. And we have two windings here, and also my stator has a balanced two-phase winding, which we are calling A and M. So yeah, if it is a like if you want to visualize this stator windings M and A, let's say this will be stator, and this is the stator, and two windings are there. We will be see how this will be placed in stator. So let's say these four are the slots in the stator. I have placed a one winding here, and let's say yeah, let's say these two belongs to coil M, and the axis of the coil M, if it is top one is cross and bottom one is dot, if the nor, bottom one is cross and dot, based on that, we will see this will be the axis coil M axis, this one. And next we will place the another winding here. This is coil A, which we're talking about, and this two coils axis will be like this. Anyway, towards the top or bottom based on the placement. And this will be axis will be same. This will be coil A axis. So this is how we are visualizing it. Okay, so the reason behind giving the terminology as A and M, we will later call these A and M as main winding. M stands for main winding, and A stands for auxiliary winding. So yeah, later we will see why it is auxiliary winding, why it is main winding, because finally we have to use this idea for a single phase machine, where in single phase only one main winding will be there. So that's why we gave it the names. So yeah, now if these two coils are supplied with a balanced two-phase currents, then they will produce the RMF. So that's the principle of a machine. We saw it in the three-phase also. Whenever when we are supplying three-phase windings with a balanced three-phase current, rotating magnetic field will be produced. Now the same holds for two-phase machine as well. So let's say the currents are like that. Let small Im, this is the instantaneous current flowing through the winding M. Im, this is the RMS, and this will be the max will be maximum current. Im max cos omega t. So this will be the instantaneous current flowing through the winding M, and instantaneous current flowing through Ia will be Ia max cos, because these two are balanced, so these two windings will be separated by an angle of 90 degrees in space, cos omega t plus 90 degrees. So if it's a three phase, we know that the three windings will be separated, displaced at an angle of 120 degrees. So similarly, this is a two phase machine, so they will be separated by 90 degrees. Now, let's say balanced currents. So if let's say these two currents are having the same magnitude. Now, if these both are equal currents, Im max and Ia max is equal to, let's say, I max, same current. Now, yeah, this rotating magnetic field will be produced in this machine, and this rotating magnetic field will move from, as we discussed for a three-phase machine, it will move from leading phase to lagging phase. Now here the A is leading and M is lagging. So the produced RMF will move from A to M. So this is let's say we are passing IM here, and this is IA here. So it will be responsible to generate rotating magnetic field, which we are calling it as Fs. It will rotate from leading to lagging. So it will be rotating in this direction, and the speed of the stator field will be synchronous speed, that is Ns. Ns we know it is 2F by P in RPS. So F is the supply frequency and P is the number of poles of machine. Same discussion. We are just repeating it for a two-phase induction machine. Now the speed of the field is synchronous speed is Ns. So therefore, once this field is produced, this is produced by my stator. And see, Once I produce this field, my rotor is just sees this rotating magnetic field. It is unaware whether it is produced by a two-phase winding or three-phase winding. My rotor doesn't know it. It just sees the rotating magnetic field. That's what rotor windings will see. Now, therefore, the torque will be produced, and similarly, we can do the discussion with how we can go for the equivalent circuit can be drawn, and the same way we did for three-phase winding. Now, this motor will accelerate in the clockwise direction, and finally, my rotor will settles to its speed, which is nr. And then we can go for the per phase analysis, which we did for the three-phase machine, and we can discuss how the air gap power will generate, and eventually we can derive the torque expression. So all analysis will stay similar. So that is okay. Now, but why people don't usually use this two-phase machines is because we have the three-phase supplies very popular here. So that's why we have a three-phase supply. That's why three-phase induction machines are very popular. Now, if we have a two-phase balanced induction machine with us, of course, if we want to rotate it, we have to convert this three-phase supply into two-phase supply. So if you remember the discussion in the transformers, or you might have heard this kind of connection, which people call as Scott connection. So in transformers, you might have heard this kind of name. So basically, people use this kind of Scott connection. So what that will do, it will convert a balanced three-phase supply to a balanced two-phase supply. It's used for the conversion. And then, if you want to rotate a two-phase induction motor, we will connect this particular motor towards uh, like after this cord connection. So that will give us a balanced two-phase supply. Now, yeah, that way we can run it and we can do the analysis. Even the torque speed characteristics also. So we have seen this is, let's say, torque slip, and this is equals to 0, and this is equals to 1. Slip will increase in this direction. So even the torque speed characteristics also will stay same for this motor. So yeah, so therefore, how can we use this idea to analyze a single phase induction machine? So that's the whole idea of today's discussion. So the idea is any unbalanced two phase current or any voltage or uh, any quantity, we have heard that about sequence components that we might have heard, right? So what are those sequence components? So the idea behind using sequence components is any kind of unbalanced system can be broke down into balanced components. So that we call as a sequence components. So let's say we have a unbalanced two-phase system of currents or voltages and anything. Uh, they can be shown to be consisting of two balanced system in it. So each unbalanced system can be broke down into balanced systems of positive sequence and negative sequence components. So that is the sequence components we call. So a two-phase quantity, let's say we take a current and we can break down it into positive sequence current and negative sequence current, which individually is balanced. So that's the idea. An unbalanced system we can break down into a positive component and negative component, which will be individually be balanced. So we know that in a three-phase unbalanced voltage, if we have a three-phase supply, and if it is an unbalanced current or voltage, that we can break down into a balanced system. So there will be three components in a three-phase system, that is positive component, negative sequence component, and zero sequence component that we might have heard. So yeah, that idea we will use it here. Now, if at all a circuit is energized from such unbalanced three-phase voltage, how to find out the currents? So let's say we have an unbalanced three-phase voltage and we need to find the currents. So what we will do is we will break down those voltages into sequence components. We will find the like let's say positive. We have a unbalanced three-phase voltage. We will break down into positive sequence and negative sequence and then zero sequence. And let's say if the phase sequence of my main unbalanced voltage is ABC, now my positive sequence will have the same ABC. Negative sequence, phase sequence will change, reverse ACB. Anyhow, this zero sequence will don't have any phase. Zero sequence means co-phasors. Like A, B, C will have same phase. There is no phase difference. So yeah, the idea is we will break down our unbalanced voltage into positive sequences, and individually they are balanced. All positive sequence components are balanced, negative sequence are balanced, and also zero sequence are balanced. So this is the idea, and then we will find the voltage. We will divide by impedance, and we will find individual balanced currents. So from this we will find the current, and then we will add up all at the end to find the total uh, current. So it is flowing in the three phase. So that's the idea. Now, in case of a two phase, so this is for a three phase voltage, unbalanced three phase voltage. Now, in case of an unbalanced two phase system, there is no zero sequence. So, similarly, for a if it's a two phase, we will have only positive sequence and negative sequence. So yeah, we will have only two phases, two components, sequence components, that is positive sequence and negative sequence. There will be no zero sequence. Now we will be applying this idea to a motor with two windings, that is main winding and auxiliary winding, and we will see how we can go for the analysis. Now, if we see that, let's consider the motor. This one we have here, and this is the main winding. This is the auxiliary winding. So these are the two windings which we are considering. So this is motor is having the two windings. Say we have currents passing through it, IM and IA through it like that. And yeah, they need not be balanced. That's the whole point. If we have a two windings, two phase windings, which are unbalanced. This current might be unbalanced because I'm not sure if I'm supplying with a balanced voltage. Now, the idea is we can break these currents down into balanced, balanced components. Suppose this IM and IA, these are unbalanced, maybe of different magnitudes, different angles between them, and may not be the angles might not be 90 degrees between them unbalanced. That's the meaning of unbalanced mean. So now I can break down this IM and IA into sequence components. Now see how I will break down this IM. I'm writing this IM as IM1 plus IM2, where 1 stands for positive component and 2 stands for the negative components. Now, similarly, IA I'm breaking down as IA1 plus IA2. Now, 1 positive sequence, 2 means negative sequence. Now, this idea or this concept we are trying to apply to our single phase machine. Now, let's see how we can do. Actually, if you pay attention, this will be a very pretty interesting discussion. How we are going to apply this discussion to a single phase machine. Now, let's consider we have a single phase induction machine where it runs on a very only single winding. That's the final point. I have a machine short circuited and only one winding I have, right? This is the main winding, and I'm supplying this with a AC supply that will flow IM in the machine. So this is the uh, my actual figure how a single phase induction motor will look like. Now I am trying to apply this sequence components concept to this. What I will do is I will do a small change which will be a similar kind of arrangement. Now, please tell me whether the diagram I am drawing it now is similar to this situation or not. I will have a rotor. Again, winding will be there, short circuited cage rotor, and I have a main winding to which I am giving AC supply. Till now, both are same. Now I am imagining there exists an another winding. I'm just making a situation where it is similar to a single phase. Now I am not supplying it with a voltage. I am not giving it voltage, and I am assuming it to be an auxiliary winding. So here my current will flow. I am assuming the current flowing through the winding is zero. Auxiliary winding current is zero. So I am exciting only my main winding. So if you see here, my rotor is short circuited. Uh, there is a main winding M and there is another winding A, which we don't excite. So, but we are placing that winding. I mean, imagining that winding is in quadrature with the main axis. Quadrature means at a 90 degrees disposal. So that is the first assumption I am making. And the second one is I am exciting only my main winding. If you see the picture, I can see I am supplying only my main winding with the supply. So I don't see any difference between the first figure 1 and figure 2. So both figures are same. I have just introduced fictitious winding, auxiliary winding, which I am not exciting. So it doesn't make any change. So both situations are same. Now, when we excite the winding M, it will definitely carry IM. I'm exciting with, let's say, VM, and it is making the current flow IM. And similarly, I have VM, I have IM, and IA is equals to 0. So this is the condition I have. So I can say this is like a balanced two-phase motor with two windings, main winding and auxiliary winding, because I have given two windings and I am assuming both are placed in quadrature at 90 degrees, and I can say this is like a balanced two-phase system. I have two windings, main winding and auxiliary winding, and my of course my main winding is carrying current IM. My auxiliary winding is carrying current IA, which is zero. I'm just terming it as an IA, but the value is zero. So the IM and IA, uh, they might be unbalanced two phase currents. So now this is what I'm assuming. So I have VM, I have IM, I have IA, which is zero. With the idea, this idea of balanced currents, I'm trying to apply it here. Now what I'm doing is I am breaking this IM into sequence components. Same thing, I'm writing it again here. IM is IM1 plus IM2. So IA, I'm breaking it out IA1 plus IA2. Now, these two, if you take IM1 and IA1, so these two are balanced two-phase positive sequence currents. These two are balanced two-phase positive sequence currents. And if you consider these two are individually balanced again. So yeah, these two might be unbalanced. These two are definitely there. I'm not sure. They need not to be balanced. These are unbalanced currents, two-phase currents. Now, this is a balanced two-phase positive sequence currents, and this is a balanced two-phase negative sequence currents we have. So yeah, now we have somehow created a very similar situation like a single phase machine where we have introduced a fictitious winding and we have imagined no current flowing through it so that I can implement this sequence components concept here. Now let's see how the phasors of this will look like. phasor diagram. A simple, very, it's not a very complicated one. I'm just drawing it. So let's take a positive sequence. I'm drawing it, and here we can see for the positive sequence, this auxiliary winding A is leading M. We have placed auxiliary winding first. So auxiliary winding is leading my main winding by 90 degrees. So this is IA1 current. Of course, it is zero, but I'm just drawing. If this winding is having a phasor, this is how it would look like. And IM1. So these two are positive sequence currents. These two are balanced and having a equal magnitudes displaced by 90. This is 90 degrees. These two are having equal magnitudes IA1 and IM1, and the phase sequence is IA1 is leading the IM. Now, if we want to draw negative sequence to it, I know in negative sequence my phase sequence will be reversed. So in here my main winding would be leading and auxiliary winding current would be lagging. Still they are 90 degrees displaced. So if this is the same axis for my main winding, if it is IM2, this would be IA2 because here IM2 is leading, IA2 is lagging, and again 90 degrees, and these two are same magnitude. So these two amplitudes might not be equal to these two, but individually they are of same magnitude, and negative positive sequence are same magnitude. So positive and negative need not be same, though they can be different. Now here we can see from the diagram my IM1 and IA1, they will form a balanced two-phase system with a phase sequence of AM. If it's a phase sequence is AM, so then my IM2 and IA2, they will form an another balanced two-phase system, but with the phase sequence reversed. It's MA for them. So my auxiliary winding current will lag main winding current in negative sequence. That's what we are seeing from the figure. Now, what are some more conclusions we can draw from the figure? So that from the phasor diagram, if you can see from figure, we can say my IA1 current, this particular current, is nothing but a 90 degrees displaced from IM1. So J, we all know J is 1 at an angle of 90. So IA1 is nothing but J IM1. So that's clear from the diagram. Similarly, IA2 is at a J, but negative J from the IM2. Right now, therefore, I am just trying to write all my auxiliary current terms in terms of main winding because finally we need everything in terms of main winding only. So that's the final winding which we see in a single phase. There won't be any auxiliary. So, but we know Ij bar is equals to Ia1 plus Ia2. So just we have this relation. Unbalanced Ia is equals to positive sequence Ia plus negative sequence Ia. Now I'm just trying to replace IA1 and IA2 here. Now J IM1 minus J IM2 is equals to Ia. But what is our assumption about Ia? Ia doesn't exist. You see here Ia is equals to 0, right? Now if I substitute Ia is equal to 0, I can say that IM1 is equals to IM2. If at all it should represent a single phase induction motor, there should not exist any current such as IA. Now I have replaced IA equal to 0 here, and by substituting it, and I have, but IM1 is equals to IA2. That's what we arrived at situation. But we know IM is equals to IM1 plus IM2. But we found that these two are equal. So therefore, I can write Im1 is equals to Im2 as Im by 2, right? Because both are equal and having the same magnitude then. Yeah. So this is what our uh, conclusion is from the phasor diagrams and also the our whatever our hypothesis is, there should not be any current flowing in the IA, and we substituted that from the phasor diagram, and we got this conclusion. So my main winding current is nothing but a positive sequence and negative sequence current summation, which are nothing but equal in magnitude. That is Im by 2, half of the main winding current. So half of the current will flow in the positive sequence, and half of the current will flow in the negative sequence. Now, what I will do, I will consider each sequence. It is first I will consider positive sequence and see what will happen, and then I will consider negative sequence and I will see what will happen. Yes. So let's consider first positive sequence. Now for positive sequence, let's say this is my binding and this is my main winding, and this is the auxiliary winding, and here I have IM1. So this is what positive sequence current is. And similarly here it will be IA1. Of course, it's J times of IM1. I'm just trying to represent here. So this is IA1 and this is IM1. And see, if we see these two currents, these two IA1 and IM1 are very balanced currents. We know that that's a point of breaking down into positive sequence. So here these two are balanced two phase currents. So what they will produce? They will produce rotating magnetic field. So yeah, with this IM1 and IM1, let's say rotating magnetic field is produced. Let's say it is called as F. And now what would be the direction of this field? So we know that RMS rotates from leading to lagging. Now here A is leading and M is lagging in the positive sequence. So we know that in positive sequence, the phase sequence is AM, and in negative sequence it is MA. It is reversed. Now in the positive sequence, my rotating magnetic field by the stator will rotate in this direction, and the speed will be ns, which is equals to 2f by p rps. Okay, now we have considered the positive sequence first, and we have seen these two currents will produce an RMF, and the direction will be leading to lagging from A to M. Now, if I consider negative sequence first, second, now I have a rotor, and then similarly I have auxiliary winding, and I have main winding, and I'm trying to pass IM2, and here I have IA2, and yeah, we have a rotor here. Here also we have a short circuited rotor, and now again these two are balanced individually, balanced two phase currents, and they will also produce the rotating magnetic field, and they produce rotating magnetic field, and the direction would be from leading to lagging, where here my IM2 is leading. So from the figure we can see IM2 is leading, so it will rotate from IM2 to IM to A, and the speed will remain same. It is increment speed to F by P, and my rotating magnetic field will be direction from leading to lagging, where M to A. Now these two cases, positive sequence case and negative sequence case, if I add these two cases, that will give me the our case, which is a single phase induction motor with main winding alone, but not auxiliary winding. So that's the case. So if we just add up these two, and then I can arrive at my single phase induction motor case. Now, let's say now we are trying to rotate our rotor with some external force in clockwise direction. So because till now we say that there is no starting torque for my single phase induction motor. Let's say I'm trying to rotate my rotor with some kind of external force in clockwise direction, and the speed will be rotor speed will be now nr, right? Now if you see the positive sequence diagram, I am trying to rotate my motor in clockwise direction, and here I can see the field direction also in the same clockwise direction. So in the positive sequence, you can see this field, it is in clockwise direction, and here the field direction is will be in anti-clockwise direction. Now, if at all I apply external force in the clockwise direction, as I mentioned earlier, now my positive sequence field will be in same direction as my external force direction, that is clockwise, but my negative sequence field will be in the opposite direction. So that we will write here for positive sequence direction of F S1. I'm writing a stator field of positive sequence 1, and my NR, that is the rotation of my rotor, which I am rotating by using an external force, that is using a prime mover or something. So both are in same direction. So this is what I'm calling as I'm naming it a name by using here the direction is clockwise, and I'm naming it as forward field. Actually, we are discussing this analysis using a double field revolving theory. So that's the theory usually can be used for the analysis of the fields produced. That's what we are saying. We have two fields that we will see. For the positive sequence, we have a forward field, and for the negative sequence, we will see it's in the reverse direction. So we will call it as a backward field, and we will proceed with the analysis. So forward field Fs1 we are saying. Similarly, for the negative sequence, see the direction of Fs2 and Nr is opposite direction. So my Fs2 is in anti-clockwise, but my Nr is in clockwise direction. So we are naming it as backward field. Now, yeah, we will call Fs1 as forward field and Fs2 as a backward field. Now, if we analyze these forward field and backward fields, and what is the slip in this condition, what is the torque developed in this condition, we will see a very interesting discussion. Now, so let's say this is my Fs1 forward field, Fs1, okay, and this is my synchronous speed, and this is my NR. So both are in same direction. Now, this is positive sequence, and let's say I'm drawing it for negative sequence. So this is Fs2, but here my direction will be here Ns, but still my NR external force in this direction. So this is for a negative sequence. So that's what I'm trying to write in the words in the top. So that's what this figures also implicate. Now, what will be the slip in this condition? The formula for slip is Ns minus Nr by Ns. It's the same formula. Here Ns is in positive, so same thing, everything is same. Now to calculate Nr, we know Nr is equals to Ns into 1 minus S. So if you substitute it here, the slip we will get is S. In positive sequence, the slip remains same as in the actual condition. Now if you see the slip for the negative sequence, we know the slip is equals to Ns minus Nr by Ns, but here the Ns is in the negative direction. Now we take minus Ns minus Nr by minus Ns. But we know Nr is equals to Ns into 1 minus S. So if you substitute it in the top, minus Ns, Now, if we solve for the slip here, we will find that the slip value will be 2 minuses. It's some kind of in the generator mode or something, or we don't go that, but here we can see for the positive sequence, the slip we got is in the S, and for the negative sequence, we got the slip to be 2 minuses. And similarly, if we see the torque generated in the forward field, which is this forward field, TEF will be in the same direction as FS1, and the torque generated here will be, we call it as a TEB, backward torque, and it will be the same direction as FS2. Now, if you are trying to find the net torque, T net is equal to this is in the forward direction, and this will be in the opposite direction. We will take the difference of those two, TEF minus TEB. So yeah, this is how the slip values and the torque values of these two systems would look like. For the positive sequence, the slip is S and torque will be same direction of Fs1. For negative sequence, the slip will be 2 minus S and the torque will be TEB, that is a backward field torque. Now let's let's have a look at the equivalent circuit of these two sequences, and here the discussion gets very interesting, and I want everyone to pay attention. So it's very similar to the induction motor equivalent circuit, but just a small interesting discussions we will make. Now, how will the equivalent circuit of these two sequences would look like? Now, first I'm drawing for the positive sequence, and see here. Now we will have a resistance as in the stator, same one, R1, X1 we will have, and here we will have magnetizing branch, and here yeah, we will have X2 dash similarly, and we will have a R2 dash by S. So this is R1 and X1 and JXM, and it is X2 dash, and this is R2 dash by S. S is the slip here. Since my slip in the positive sequence is S, I have noted it down as a S. But now, you know, in the negative sequence, it will be what? It will be 2 minus S. So if, okay, first I will complete this circuit. So here I am giving VM1, and I am expecting a current of IM1 to flow here. Yeah, and we know this IM1 is equals to IM by 2 in case of a single phase machine, because we assumed IA to be 0, so that IM1, we already see that discussion. So yeah, now similarly for the negative sequence, R1, X1, and there will be a parallel branch, magnetizing branch, and X2 dash, and this is the resistor. R1, X1, and X2 dash, and this is JXN, and here it will be, here we have to pay attention, it is R2 by S. This is not R2 by S, but it is a R2 dash by 2 minus S, because that's what we found in the negative sequence. The slip is 2 minuses. Now again we are expecting a current of IM2 to flow when we apply VM2 voltage. Now again IM2 is equals to IM by 2, right? In the both sequences, IM1 is equals to IM2. So we are already assumed the current to be equal and a half, but from the empirical relation we got that. So both currents are equal here, IM by 2 and IM by 2. So, and the interesting thing which we have observed is the change we are going to make here is, now both currents are taking same current, IM and IM. So we can just connect these two in series, because if we connect these two in series, then also same current will flow. So that is a very interesting idea to implement it here. So finally also our main aim is to add these circuits and find the analysis. One second. So the idea is to add these to an analysis, but but to help with that discussion, we have found that both these sequence equivalent circuits are having the same current. So there is no harm in adding these two and or connecting these two circuits in series, because same current is flowing in the stator windings. That's what we observe from the diagram here. So what I will do, I will connect these two in series. So this, sorry, I'm just connecting these two. I will extend this one. So here it will be giving the total voltage, and I will connect this to here, and total VM will be here, and this will be connected to here. So this is VM2 and this is VM1, and these two are in series, VM1 plus VM2, and it will be equal to VM here. So that is the total voltage we are applying, and the same current is flowing here. It's I1, and it is comes like this, and again it will go to like this, Im by 2. Here same current, and here also same current. So we have somehow connected these two equivalent circuits of positive sequence and negative sequence in series, and now we already discussed T net is equals to forward torque minus backward torque, and we know the formulas for torque produced. If you remember the discussion in the three phase circuits, we know that torque in synchronous watts, of course, 3 I2 dash square multiplied by R2 by S. This is the torque expression, divided by 2 pi ns will be there. But in synchronous watts, it's same as air gap power. 3 I2 dash square R2 by S. I2 dash square is what? The current flowing through the resistance of the rotor, right? So this current and this current. Now, if I want to calculate the net torque here, what I will get? T net is equals to, this is very important, torque forward minus torque backward. So if we assume the current flowing through the R2 by S in case of positive sequence as IF, that is IF1, forward field in the positive sequence, assuming, and assuming the current flowing through this negative sequence is IB, because backward field it was IB1. Now my forward torque would be equal to, is here 3 means for a 3 phase, here it will be for a 2 phase, 2 if1 square multiplied by r2 dash by s minus 2 multiplied by ib1 square multiplied by r2 dash by 2 minus s. So yeah, this would be the formula for my net torque. So let's give a equation A to it. So this will be a important relation which we will be using it later. So this is what my single phase induction machine torque expression would look like, if at all it is having a positive sequence circuit and also negative sequence circuit. So this is what we have seen, and also we have Vm here, where Vm bar is equals to Vm1 plus Vm2. So this is also another important relation. So yeah, and if we compare this particular equivalent circuit, so we have applied a Vm and Im by 2 current is flowing, and let's compare it with the original circuit we have. What is the original circuit? So this one. So we have applied Vm. So let's draw it there itself so that we can have a good comparison. Now this is what gets interesting here. See, this is my rotor and this is my main winding, and I have supplied with Vm, and then the current of Im will flow through the stator, and this is the main winding, and this is my single phase induction motor would look like. So for this circuit, we have drawn the equivalent circuit, right? Now let's compare this circuit and also the equivalent circuit. Now we have VM. Okay, VM is okay. We have given the entire supply as VM, and then it should make the current flow as IM. But what is disturbing us here? The series current flowing through the stator is not IM, but if you see it is IM by 2. So that's what it's disturbing for us. If if we can somehow make this current IM by 2 as IM, so if we want to double the current, then my equivalent circuit will have no problem. Everything will match. Everything will be okay, and I will also be happy with it because my original circuit is having components like VM and IM, but my equivalent circuit is having VM but IM by 2. Now both should match. Original circuit should equivalent circuit should exactly replica of my single phase induction machine. Now what can be done? So how can we change this IM as IM by 2? Sorry, IM by 2 as IM. So if we want to double the current, we know this VM voltage divided by all impedances, whatever it is, the total is giving us IM by 2. So how to double this current? So one easy and obvious way to double the current is, let's half the total impedance. If all the impedance in the circuit are halved, like if we divide all the impedances present in the circuit by 2, then definitely my current will go twice up. That's it, right? So I will do, I will z by 2, so that I will multiply by 2 in the current, so my current would become IM. So that's the idea. Now keep, keeping the voltage same. Okay, now keeping the voltage same, if somehow I can make the impedances as half, then I can make the total current flowing through the circuit as a IM. So that's the idea. Yeah, so I can discuss it further, but we are already at the 5:30. I also want to discuss some problems with you all. What I will do is we can continue this discussion and pick up the thread the next week. So the idea is, that's why I hope you understand the discussion now. So we are trying to make the equivalent circuit for the single phase induction machine. So what the idea what we did. So anyhow, we to analyze any machine, we need to do it from equivalent circuit only. So we came to find that my single phase induction machine can't have a starting torque because there is no another field for it, and whatever field which is having stator field and rotor field, they are acting along, and they should be displaced in order to have a torque. So we find that starting current is not there. So to enable that, so we are assuming there is a fictitious winding, auxiliary winding, and we are assuming it as a two-phase system. Now, if we know, if we have a two-phase unbalanced system, we can easily break down into sequence components, and then we proceeded with the analysis, and then we came to a final equivalent circuit where it resembles almost, we have to the original circuit, that is VMIM, and here we have VMIM by 2. Now we got the discussion of making the impedance half, so that we can have the current of IM flowing through it. So what I will do next week, we will discuss the exact equivalent circuit by halving the all the impedances, and then we will arrive at the final equivalent circuit, and then we will calculate the torque in the equivalent circuit and also the air gap power inside the circuit, and we will actually compare this equation A here, what we will see, we are seeing on the screen, equation A, with the derived equations of torque and air gap power, and then we will compare these two, and we can actually see the difference. So how my exact equivalent circuit expression would look like, and we can also verify that expression like that will actually represent my single phase induction machine. So because that equivalent circuit, if we substitute the starting condition, starting of the motor conditions, so what are the starting slip is equals to 1. So if we can substitute the s equals to 1 in those torque equations, we can see actually when we substitute s equals to 1, my total torque would be 0. Then only we can say at starting torque is equals to 0. And if we go for any other slip that is under running condition, we can see we get some actual torque in that. So yeah, we will see all the discussions in the next week. So we will close this single phase induction machine discussion even better there. So yeah, let's go and discuss some problems first, so that it will help you solve the assignment as well. So we have half an hour left. So let's start discussing the problems. So I would request everyone to pick up pen, paper, and also calculator with them. So yeah. So this problems which we are doing today will be based on the starting of the induction machine. 2 weeks back we have discussed the starting methods. That is direct online starting, auto transformer starting, reactor starting, and also star delta starting. So we will be applying those concepts here, and we will see how we can solve the questions. Starting of the induction machines is very simple. So the idea is, using these starting methods, we are actually reducing the starting current burden. So let's say we have some X amperes of current at the starting. So using these different starting methods, we are actually reducing the burden on the motor. So if we use auto transformer starting, we will get some other starting current. If we use reactor starting, we will get some other current, and star delta starting, we will some get other starting current. And yeah, that's what the idea of starting methods is. Okay. With that, let's look at the question now. So the question is, a three-phase 440 volts line-to-line voltage squirrel cage induction motor. So it is having an efficiency of 80% and a power factor of zero point 0.8 at the full load. Let's try to write the given data. So it's a three-phase 440 volt machine, squirrel cage induction motor, and efficiency at full load is 80%, and power factor at full load is zero point 0.8. Okay, now the starting current at the rated voltage is 4 times the full load current. So here we can see how much more the starting current is. If there is no any starting methods, now we can see my starting current is 4 times the full load. It's very dangerous. So here it is written that I starting is 4 times the full load current, and the supply has a limitation of 1 kilo amps current, line current at max. So I supply limit, that is line to line, is equals to 1000 amps. So this is what the data they have given. Okay, now what's the question? This limitation is, my supply cannot supply more than 1000 amps line current at any time. So that's the limit of my supply. So that's what they have given. Now we have to estimate the maximum permissible kilowatt rating of the motor if DOL starting is used. So see, they are asking what is the maximum kilowatt rating of the motor I can use. It means that I will draw 1000 amperes line current from the supply anyhow. That's the maximum limit. I want to utilize all the maximum current from it. Let's say I am drawing the supply current of line current of 1000 amps. Now that will somehow have to use the entire supply limit, so that I can make a very high kilowatt rating motor. But the limitation here is, they are saying I am using a DOL starting. Now if it is a DOL starting, let's say we have some X kilowatts, and this will make some kind of starting current. Now if we use some other better starting method, and we can see actually from the numericals, we can even go for better kilowatt rating, because if we go for another starting, So the static current burden will reduce. So for the same maximum current of supply limit, so 1001 kiloamps, for the same limit, we can actually make even a better motor that we will see anyhow. So let's see. Okay, what is here the question? So maximum permissible kilowatt rating. Okay, if it is a DOL. Now, since we are using the DOL, there is no starting current burden. Whatever starting current is, it's four times the full load current. It's already there, so we can't do any change here because direct online starting doesn't have any decrement in the burden. It's just used for the small motors. That's why. So okay, for the DOI starting, we know that there is no any limit on it. Now, my full load current maximum limit, they have said that my full load current, see, my starting current will be four times the full load current. So we have to find the full load current here. So how much is the full load current limit? It's nothing but starting current limit divided by 4. Now, the maximum my supply can give is a 1000 amps. So I want to use it anyhow. This starting current limit will always be 1000 here. Okay. Now it's nothing but 1000 by 4. So since I am using DOL starting, I can only extract 250 amps at the full load condition. So that's the limit. So we will see for another starting methods how we can improve this full load current. So if we are improving full load current means we are improving the rating. Okay, 1000 by 4 it is 250. So now we got the full load current limit, and what is the required thing? Kilowatt rating. That is the output power they are asking. Output power, we know output power is equals to input. This is the limit. What is the maximum limit? So maximum input power limit multiplied by the efficiency. So input power multiplied by efficiency will give the output power. So how to calculate the input power? Input power is root 3 VL IL cos phi, right, multiplied by efficiency. So root 3, what is the line to line voltage? It's 440 volts. And here this line current limit will be, this is the full load line current limit which we calculated in this full load limit. So yeah, because this 1000 amps is the line to line supply. So this is line to line and this is full load line to line, and this current line current full load current is nothing but the 250 amps. What is the power factor of the full load? It's 0.8 multiplied by the efficiency is 80%. Again 0.8. So how much we are getting here? Please calculate it with me. Root 3 times 440 times 250, 0.8 into 0.8. So 121.936 kilowatts I'm getting. So this is the maximum kilowatt rating which I can model my motor if I'm using the DOL. So okay. So now we will see if we are using another starting methods how my kilowatt rating will be improved. Okay, estimate the maximum permissible kilowatt rating of the motor if auto transformer setting is used with a tapping setting of 75% setting. So we are setting a x. You remember the formula? Set x is equals to 0.75. 75% setting we have used. Now, if it is a auto transformer starting, how much full load current I can improve? So that we can see here. So we know from the problem I full load limit is equals to whatever permissible starting torque limit divided by 4. So that's from the problem. So any cost, my full load current will be maximum current divided by 4 times. That's given in the problem. Now, in auto transformer, what was given? X is equals to 0.75 setting. It will be always between 0 to 1. Now, we know that if I'm using my auto transformer, my full load current, my burden of the starting current will be reduced by x square. That is the formula. So IST, if you remember the formula, starting torque for the auto transformer will be x square times of I starting line current in the DOL. I hope you all guys remember this formula. So, so you can see my full load current is actually reduced x square times. Now, my full load limit uh, actually x square times of my full load current which it can give. So, in auto transformer starting with x is equals to 0.75, my IFL limit, that is IFL limit will be reduced by 0.75. So multiplied by the x square will be my new full load current limit. So this will be equal to I starting limit by 4. So by using this 0.75 settings, we are actually reducing the burden on the starting current. Now let's see how much this new full load current will be. How much we are improving this current we will see here. Now my I full load limit will be, see this is 1000 anyway. I am trying to extract the maximum permissible starting current, that's anyhow will be there, divided by 4. This 0.75 square will come this side. And how much is this? 1000 divided by 4 multiplied by 0.75 square. It is 444.44 amps. So if you see in the DOL, we got the full load limit as 250 amps only. Now, as we are using an auto transformer, we are actually reducing the burden on the starting current. So we are able to extract more current from the starting. So out of 1000 amps available at the supply, out of 1000 starting current, I am able to extract 444 amps at the full load condition. So it's not 250 amps anymore. At the full load, we can able to run my motor at 444 amps now. So for this, again, the post analysis will be saying we need to calculate the maximum permissible kilowatt. That is P output. That will be the P input multiplied by efficiency. Root 3 times line voltage 440. Line current is now 444.44 multiplied by that cos phi, power factor, and efficiency. Now, if you multiply this, how much we are getting? Root 3 times 440, 444.8 into zero point 0.8. Okay. How much you are getting? 440 into 444.8. Okay, so I'm getting 216.775 kilowatt. Please verify with it 0.75, 0.8, and zero point 0.8. So yeah, this is how we are improving the output permissible limit if we are using the auto transformer starting. So now we will see the same kilowatt rating of the motor if star delta. We finally came to the conclusion that my star delta connection will be even much better, because here we have seen that my x limit will be 1 by 3. Please go to the if you are having any confusion in the formula, just visit the starting torque, that is week 8, I guess week 8 discussion, it will be there. So star delta will actually reduce the starting current by 1 by 3 times, by 3 times. So let's see what is the permissible limit in this kind of star delta connection. Now if it's a star delta, my IFL limit in start delta is equals to I starting limit divided by 4. Now my IFL limit in start delta will be IFL limit multiplied by 1 by 3. It's with the DOL. If there is no any starting method, then it will be I starting limit like this will be the full load current which actually flows in the motor if there is no any starting method. Now we are trying to find this current, how much it will be and how much my starting will going to reduce later. Now to find this current, IFL limit is equals to this is 1000 divided by 4. It will be multiplied by 3. So how much is this? 750, right? 250 into 3. Now I am going to get a 750 amps of current here. Now for this, if we calculate the P output, P input into efficiency, and root 3 440 multiplied by 750 root 3 VLIL cos phi into efficiency is 0.8. Now let's calculate this. Root 3 into 440 750. Okay. Now here it will be giving 365.809 kilowatt. Now if you see by using different starting methods, how we are improving the kilowatt rating of our machine. So first we are having only 120 kilowatt something. Next we have just about 200 kilowatt, and by using star delta we can actually maximize our kilowatt rating to 365 kilowatts. So we can go for a bigger and bigger motors by using for different kilowatt rating. Now we also see that for direct online starter, it's actually a very small motor. It's around 120 kilowatts. So that's the advantage of using different starting methods. Now, yeah, let's go for the next question. For this, data is different. So let's see what this question is. A 16 kilowatt, 440 volts line to line, three-phase squirrel cage induction motor has a full load efficiency of 85% and a full load power factor of 0.8. Okay. Now it is given that my full load current is equals to 25% of the starting current. Okay. Full load current is 25% of the starting current. Okay. So the full load torque is 64% of the starting torque. Okay. Now the question, so again, something else is given to reduce the starting current. Auto transformer starting they have used to reduce the burden of starting current, and the tap setting, we don't know the tap setting, but they are saying that by keeping that particular tap setting, they are getting the full load torque at the starting itself. Okay, that's interesting because they have set the tap ratio such that they will get the full load torque at the starting. So usually we will get something else starting torque at this machine, and then later the starting torque will change. So but they have made the setting in such a way that they are getting the full load torque at the starting itself. So yeah, now the first question is we have to find the setting at which the auto transformer has been set. So what is the factor? Like in the last problem, we have x is equal to 0.75 setting. So in the same way, what is the auto transformer setting now itself? Okay, let's write the data, and it's 16 kilowatts, 440 volts line to line, three-phase squirrel cage induction motor, has a full load efficiency of 85% and power factor of 0.8. Now, okay, what was asked? Okay, another condition is my full load current is equals to 25% of starting current, and my full load torque is equals to 64% of starting torque. Okay. And to get so using auto transformer starting, they have got TEFL, that is full load torque at the starting condition. So this is the condition they have achieved using the uh, auto transformer starting. So what we know in case of auto transformer starting, we know the starting torque in an auto transformer starting is equals to starting torque in case of DOL or without any starting method multiplied by x square. We are trying to find this x now. Okay. Now we know that first we will look at the starting torque. Now we know that starting torque will be equal to full load torque by 0.64. That is without any starting method. That's the condition of the motor. Now we will replace this starting torque by full load torque divided by 0.64. That is what we have got it from here multiplied by x square. Now see, and using this auto transformer, what I am getting, the starting torque is equals to the full load torque. That's the condition we have set by applying this particular setting x square. Now by using the auto transformer, my starting torque is nothing but the full load torque, right? Now if you see at the both sides that full load torque will cancel. Now my x square is equals to 0.64, and from this I can find the setting of my auto transformer. That is, I am setting the auto transformer at 80% setting such that I am getting the full load torque at the starting itself. It's just a application of the known concept. And then the last question for today is, what is the line current drawn by the motor at the starting? Okay, so this I machine line current at the starting. This is what asked when it is a auto transformer starting. Now we know that so let's write the basic formulas. I hope you guys remember those formulas, or if not, you can refer to the lecture later. So I machine starting current in case of DOL. If you remember the diagram, that this is the delta winding, and there will be the current drawn. It will be nothing but V rated divided by ZSC. So in case of auto transformer, we can see that here we are getting X setting of V rated. So that will be the line voltage here. Now I will write here I starting current machine line in case of auto transformer. We will get X times of V rated divided by ZSC, right? So now from this I will write the line current drawn by the motor at the starting. That's what the question is. At the starting, I starting line current drawn by the motor is equals to, in case of auto transformer, from the this one we can see. So this particular V rated by ZAC is nothing but the starting current drawn by the DOL, that is X times of I starting line current drawn by the motor in case of a DOL DOL starting method. Now see, we know that x is equals to 0.8. We just found out that in the first question. Now we know x. So this was asked in the question. So we need to find what is the starting line current drawn by the motor if there is no any starting method. Now from the question, if you see the starting current without any starting method, this is the condition they have given. It should be full load current divided by 25%. So that relation I know. I starting current is equals to I full load by 0.25. So this is this one only that we are trying to calculate. Now, how to calculate the full load current here? Now, to calculate full load, we need to know the output power rating of the motor. So in the question, it was given that my motor is a 16 kilowatt motor. Now, 16 kilowatt is equals to my output power. We know the formula for output power, input power multiplied by efficiency. Efficiency is also given in the question, that is 85%. Now, what is the input power? Root 3 times line voltage, that is 440 volts, multiplied by the line current full load. That is what I am trying to find here. Root 3 VL IL. What is the power factor? It is zero point 0.8, multiplied by efficiency. It is 85%. So from this equation, please find full load current. Let's find full load current. 16 kilowatt divided by root 3, 440, zero point 0.8 power factor, and 0.85 efficiency. How much? 30.87 amps. So this is the full load current we are getting. Now from this, you please calculate the starting current. Now I starting current is equals to 30.87 divided by 0.25. How much is this? 123.49 amps. Okay, now we got this one. So you multiply this with the X rating setting to get the line current drawn by the motor at the starting using this auto transformer. So my required I starting line current drawn by the motor for auto transformer starting is equals to zero point 0.8 setting multiplied by this current 123.49 amps. So how much is this? It is 98.797 amps. So yeah, this is the final line current drawn by my motor at the starting condition. So whenever we are using an auto transformer, we have to keep in mind that my current will be reduced by X times my motor current, not the starting current. If you just compare the starting currents in both, uh, yeah, so that it will be X square times. But if the current drawn by the motor will be X times only. So I request everyone to just revisit the lecture video of that starting current, or you can refer to our discussion video uh, week week uh, week 8th or 7th, I guess. So you can find all these formulas there. So yeah, so that's the discussion today. So with this problem, we will end the discussion for today, and it's also 6 o'clock. So so next week we will be picking up the thread where we left today. We will discuss the equivalent circuit of single phase induction machine, and we will see the torque expression and also the power expression in the next week, followed by some more discussions. We will complete the discussion in next week. And apart from that, a quick look back at the discussion today, whatever we have discussed today. So we started the discussion with a single phase induction machine, and by looking at, we have decided that this machine cannot have a starting torque, but this machine will have a running torque. So we took that point, and we tried to analyze how to model this kind of machine using a two-phase induction machine basic principle. And for an unbalanced system, how to analyze using sequence components. We have tried to bring our single phase induction motor close to a two phase induction machine by imagining a fictitious winding of auxiliary winding and assuming no current flowing through it, which is exactly similar condition. And then we have started looking at the phasor diagrams and deriving some current expressions, and then we started making our own equivalent circuit with the found slip values and also torque values. And then we have arrived at the torque expression of this equivalent circuit. And there I want everyone to remember this point where we have tried to double the current Im by 2 to Im, so that we can bring it even closer to our original circuit by half, doing half of the all the impedances. Anyhow, we will discuss it in the next week again, so that we will have a closure of this topic. And then we started solving problems on the starting methods of induction machine. And the problems are very pretty straightforward, but you have to just pay attention to the parameters given in the question and what they're asking. Are they asking the starting current, or are they asking the full load current, or are they asking the motor drawn current or supply current? These are the basic things which you have to keep in mind. And we can see by using different methods how we can improve the maximum permissible kilowatt rating. And finally, we have seen an auto transformer starting problem. And there are five more problems for this. Those five more problems which will be related to your assignment will be discussed in the following session from 7 to 9. So please attend that session. Uh, and
Excuse me, can you show the previous problem?
which one? This one?
That, yeah, yeah. This is not. Next one, next one.
This one?
Find the required tab setting. Okay, okay.
Yeah. So yeah. So in this problem, we have to find the tap setting. So we know that in a transformer, auto transformer, it will be x square times the starting torque. So we know that starting torque is 64% times the 64% of the starting torque will be full load torque. So with that relation, we have found the tab setting. I will upload the slides and also the video in our portal, so you can check that out. So
Thank you, thank you.
yeah, thank you. So if you're having any doubts, you can ask me, and we will get back to you. Or if I'm not able to solve, I will try to attend your queries in the coming session, or you can ask your queries in the next session from 7 to 9 as well. So I thank you once again for patiently listening to the session, and yeah, thank you, Govind. Thank you, Anil. So yeah, we will be meeting for the 11th week discussion next week Saturday, Tuesday from 4 to 6. Please attend the discussion from 7 to 9 today, so that you will get to discuss the next five problems also based on this. So yeah, thank you once again, and see you all next week. Thank you, Surchi. Thank you.